This is part 4 of the ENFUSE bioelectricity module. Remember that the pulse waveform that we'll be measuring in the laboratory is fairly complex. And it can contain content at various frequencies. And these small noise signals that you see here are high frequency, and we can use filters to remove some noise and clean up the signal. The main filter types are low pass filters, high pass filters, and band pass filters. And of course, as the name implies, for a low pass filter it allows low frequencies to pass through and it stops high frequencies. And a high pass filter will stop the low frequencies while allowing the higher frequencies to pass. And then of course the band pass filter will stop low frequency signals and will also stop high frequency signals, but there is a band between the F low and F high where the signals are allowed to pass. The series RC circuits that we looked at in part 3 are actually low pass filters. And let's take a look at the photodiode as our source that we were using before. And let's connect that RC circuit. In addition to that, we're going to connect a resistance R sub L, which is going to be our load, and we're going to look at the voltage across the load, call that V out, and we'll assume, for example, that this load is our oscilloscope and R sub L is very large, semi-infinite. So the RC product, if you recall, determines how fast the filter will react to changes in the source voltage coming from the photodiode. And the cutoff frequency for our filter, so this is our low pass filter, and it has a cutoff frequency omega sub c, which is equal to 1 over the time constant tau, or 1 over the RC product. At the cutoff frequency, when omega, the frequency of the signal, is equal to the cutoff frequency, then the magnitude V out is equal to the magnitude of the source voltage V sub S, and we'll call that V sub S, times 0.707, or the magnitude of V sub S divided by the square root of 2. So if we're at frequency greater than omega c, then the magnitude of V out goes to 0. And if we're at frequencies below the cutoff frequency, then the magnitude of V out approaches V sub S. So in our pulse waveform, we talked about the fact that that actually contains some content that is at a low frequency and some content that is at a high frequency. So you can think about, for example, having this RC filter here, and we may have some low frequency signals coming into the filter, simultaneously with high frequency signals. And when these two signals pass through the low pass filter, of course the low frequency signal will be allowed to pass, the high frequency signal will not be allowed to pass, so coming out of the output of the filter is only the low frequency signal. So for a typical human pulse, somewhere in the area of about 60 beats in 60 seconds. So that's roughly about 1 hertz as a nominal frequency. So if we were trying to design a filter to clean up a noisy pulse signal, we might choose high frequency to be greater than, let's say, 4 hertz, and then the low frequency would be signals less than 4 hertz.